Hi. Now I am going to explain the test bench architecture of D flip-flop. We are going to develop a D flip-flop design, and we are going to develop SV-based test bench for verifying this D flip-flop. So this is the hierarchy we need to follow while designing. Top model is written in module. Inside the top module, we need to instantiate the design and interface, and the program block, nothing but the test bench. Then inside the program block, that is inside the test bench, we have an environment. It is written using class. Inside environment, we need to instantiate all these components like generator, driver, monitor, checker, and coverage. Then this CFG class is as like a configuration database which is used in UVM. Right here we are creating one class to store the values, and wherever we need we can access from this class, config class. And this is nothing but the transaction, or we can call it sequence item. With the help of the transaction in generator, we are developing this sequence, and we are putting into the mailbox, this indicate mailbox. Using this mailbox, we can able to transfer the transaction from one component to another. Here I am sending from driver, sending from generator to driver. This driver will convert this transaction into a pin level signals, and through interface the signals are passed to the DUT. The monitor capture all the in and out transaction transfer happen between the DUT and driver, capturing through the interface. And the pin level signal again converted into transaction level signal, and it is sent to the coverage and as well as checker or scoreboard through this mailbox. Here we see the code. This is the DUT, D flip-flop, module name and port list. Here inputs are D clock reset, output is Q bridge. Here I use a behavior modeling, so output is declared as a bridge. Then always at passage of clock, when reset is 1, output Q is 0. When reset is released, whatever you are giving as an input D, then comes to the output Q. Once the design is done, we are going to start developing the verification structure. So module top, this one. Now we developed this one. Now we are going to develop this top model. So inside the top model, we need to generate the clock and reset, and that is passed to the interface, and through interface we are sending that to the DUT, and the same clock reset is used everywhere in the design. So clock and reset are declared here, and here in this initial block I generate the clock, initial clock equal to 0, for our as5 clock equal to not of clock. So it will generate a clock signal with the time unit 10 as 10 timing. Then reset, I make reset as 1. There's another initial block, I make reset as 1, and after as 20 time unit, instead of that here I used synchronous delay, repeat 2 at passage of clock. So passage of clock will happen 2 times, then reset becomes 0. Then after 100 time unit, I'm going to finish this simulation. Then this initial block is used to get the test case from the command line output. So this test case I declared df of CFG. The df of CFG is the class. Inside that, I declare a test case as a string, and that I declared as a static. So when you declare a variable or a field as a static, a common memory will be created. Okay, wherever you need, you can access from that memory location. Now, where it is present inside df of CFG. Test case is present inside df of CFG. And one more thing here, all the properties I declared as static. Okay, so when you use need to access anything inside this class, directly you can access through this class name. Class name scope resolution that field. Here, this dollar value dollar plus args is used to get the argument from the command line. So that is assigned to test case, which is inside df of CFG. Here I just display what I received in the command line. Then here, see, inside the top, we instantiate three things. One is DB, another one is interface, another one is model. So here I instantiate the design. The design model name is DFF. That I instantiated here, DFF as DUT. Under this mapping, DUT. So before that, I'll explain this one. Interface class. It's not a class. Interface block. Interface and then interface are keywords. DFF int is the name of the interface block. Here, in the interface, we should declare all the input and outputs we are going to use. So this here we should declare those as logic, because in System Verilog we have a logic data type and hold 4 states 0, 1, etc. In design, if you see, we are going to use only two state data types. In DUT, if you see, that is in Verilog, we are using 4 state data types 0, 1, XZ, it will support. In Testbench part, in System Verilog, we introduced 2 state data types. Okay. So that performance will be high, memory consumption will be low. So to support these two, it may give the output X or Z. Okay. But if you use a two state, you don't know what is X and Z. To receive that, in interface, all the signals are declared as logic. So in interface, clock, reset, D and Q, all are declared as logic. Here, clock and reset, we are generating at the top module, and we are passing to the interface INT. The clock and reset we are generating and we are passing to this INT. Here we are receiving. You see in the DFF, it is declared as input. Clock and reset we are receiving. And this is the design we instantiated. We need to map the signals. There are in design we have these 4 signals. Okay, these 4 signals are mapped to the interface signals. Clock is nothing but the design in clock. So these are the design signals dot reset and this D and Q. So inside the bracket we are mapping to the interface signal INF dot clock, INF dot reset, INF dot D, INF dot Q. And one more thing, here I instantiate the interface as INF. Okay, this INF, okay, here I instantiated as INF. This when I inserted this inside the model, this is the actual physical interface. Memory will be created for this. For example, 100 location will be located these interfaces. This handle, this location, I am setting in CFG as a virtual interface. So these config and these blocks are written using class or dynamic in nature. So inside a class, you can't able to access the physical interface. The physical interface is static in nature. So with the help of virtual interface, we can able to access the actual interface type, physical interface. So for that, I am setting the location or handle in the config class. So wherever I need, I can access from this config class. So this setting I am done here. Initial beginning. INF is the handle pointing to the actual physical interface I initiated here. This one I am assigning to VAF, which is present inside DF of CFG. DF of CFG, inside that you see DF of INF using virtual keyword I inserted as VAF. Interface, this one I inserted as a virtual interface. I named the handle as VAF. For this VAF, I assign the actual physical interface. So 100, when I inserted, assume that 100 location, the handle is pointing to 100 location. That 100 now I assign to VAF. Okay. So wherever I need, from here I can able to access the physical interface. So here I declared as a static so that it will be located in a common position, common location. Now we are moving to next level, that is TB. It is written in the program level that I am instantiated here. TF of TB is the program block name that I instantiated as TB. Then before that, I will explain what is a transaction. So transaction class. So inside the transaction class, we should retain all the input outputs used in the design. So inputs you should declare as ran so that you can randomize the inputs. If you want constant, you can write constant here also. Now we move to the Testbench TB. It is written inside the program block. Why we are writing this as program block? Because this program block scheduled in the reactive region. DUT will operate in the active region. To avoid when the execution of design and test bench happen at the same time, there's a chance of missing the signals, capture or receiving the signal data. The, we may not receive at proper time. So to avoid that, we are using this program block. It will operate in the reactive region. So inside the program block, we instantiated env. See the df of env is the class name of env that we instantiated as env, and with the help of new of we are creating the object for env. When you create an object, allocate a memory, then only you can able to access the methods and properties which is available in this env. Here inside the initial block, I am accessing, I am calling run task which is present inside the env. Here, this is class df of env in class. Inside the env class, we need to instantiate all these components. Generator, df monitor, checker, coverage. And inside the run task, we in fork join, I am calling all the run tasks parallelly. Fork join is used to call all the run tasks at the same time. Okay, now we will move to the generator. So generator, with the help of transaction, we are going to generate the sequence. So here, when I need to start to generate the sequence, once the reset is released, I need to start that. So how I can access the reset? Reset is our interface. So to access the interface, I need to get the interface, virtual interface handle from this CLG class. So here I initiate the transaction as a dx, dx is the class name of the transaction class that I instantiated as dx, and here I instantiate the virtual interface, virtual dff int VAF. For this VAF, I need to get the handle which is present in CFG VFF CFG. Inside the run task, see here, I am getting this VAF is nothing but this VAF handle we created. For that, we are getting the actual handle which is present in VFF CFG. Once I get this, I am waiting for VAF. Inside VAF interface, we have a reset. I am checking when reset is 0. Under that, I am waiting here. When it is happened, and start generating the transaction. Here I create a new for dx, nothing but instance of df/dx. Okay, I create a handle. Here I create an object for this, and dx.randomization method is to randomize the inputs. Here this is an inline constraint. I'm using the distributive constraint. So randomize with d dist. I'm giving the weightage for 1 to choose 5, and for 0 choose 5 times. And then once it is randomized, when the transaction is randomized, I need to put the transaction into the mailbox. So mailbox I need to create. So that mailbox I already created in this DFF config. Mailbox keyword mailbox gen to BL is the mailbox name, and new of is used to create a memory for this. Here I declare this as static so that it will be located in the common memory location. So here I need to, if I want to access this one means with the help of this class name BFFCIG scope resolution gen to BFF. Then I use BFFCIG scope resolution gen to BFF dot put. Put is the method associated with the mailbox to put the transaction in the mailbox. Then so here in generator we are going to develop different test cases. So in the inline command, if I give test case name as write read, here it is getting the help of $value $+. So now the test name is write read. Generator, I am checking that one inside the case statement. That should be inside the run task. I am checking test case name. So this is available in BFF/CH. So if it is write read, it will perform this operation. To write any some other test case like read. When you pass read, if you write a read sequence, that will be called and that operation will be takes place. Now moving to the VFM, looking at the driver. Through mailbox, it will receive the transaction and it wants to convert that into P-level signals, and through interface, it will try to the class VFF inside that I inserted VIF virtual interface handle because I need to access the interface, right? Then only I can able to transfer the signal to the interface. And VF of TX. I declared it because I through mailbox I am receiving the transaction TX. So this VF should know what is TX. So I declared TX here, and inside the run task and get the actual virtual interface handle which is present in VF of CFG. Okay. Now I get the handle and inside forever loop. Okay. Here forever I am using because continuously it is checking. As soon as when I put the transaction to mailbox, here I need to get it. So this is the mailbox used to put this generator, the same mailbox. Using get method, I am getting the transaction TX, which is here. I want to drive it to the DU. So drive is a task. I will go here. Task drive inside that at each passage of clock tx.d. So tx is nothing but the transaction side we have a d that is assigned to VIF, nothing but interface, and the interface we have d, right? For that I am assigning. So now this is the transaction signal is converted into pindover signals. Next is monitor. Monitor we need interface handle because the interface only we are getting the data, right? So with the help of config class, I can able to get the virtual interface handle. See, I instantiated it here, and inside the run task, I am getting the actual interface for this field. And forever loop at each passage of clock is VIF.d. Now I can able to access the interface. So this interface I can able to access is VIF.d and VIF.q input and output I am getting, and I am putting into the transaction. I am assigning that to transaction.d and transaction.q. So this TX we need to instantiate before using, and we need to create a memory for this. Only you can able to store the values here. Once it is converted into a transaction method, we need to put into the mailbox. So from here, I am sending the coverage as well as checker. I need two more mailbox that also I declared in the config class. Mailbox mount to cover and mount to checker. And I created a new here. So directly I can access the monitor. Mailbox is present in VF of CFG. With the help of scope resolution, I can able to access the mailbox. And using put method, I put the transaction. And in checker, I am getting collect from the mailbox with the help of get method, and I need to compare the input and outputs. Inside the run task, it should be inside forever. That means it will check. I continuously check for mailbox any transaction is there or not. We using get method, we put okay, using get method we can get the transaction. And after getting that, here we are checking tx.d equal to tx.d. If it is matched, equal to q, this is correct and it's printing the enq value. Else, if it is mismatched, it will throw an error and it will showing the expected and actual with q and d values. Coverage. So coverage also we are getting, and we need to hit the pins based on the signal. So in coverage, inside the run task, inside the forever, we are collecting the transaction using get method. Get to CLG mount to cover is the mailbox. Using get method, we are getting TX. Once TX we get, I am triggering the cover group. Okay. Dot sample is a method used to trigger the cover group. Cover group name is DFMCG. Here I wrote it. Cover group. Cover group name is DFMCG. Inside cover group, you need to write cover point. So cover point name here I gave us out. The tx.q. Here I am getting tx. The cover point what I am checking tx.q. When this q is 1, it should hit this bin. So bins 1 and bin 0 I created. When this bin 1 will hit, when I receive 1 tx.q. When I receive tx.q as 0, it will hit this 0 bin. So the coverage is used to check how much specification is covered, how much functionality is covered in the design. And this new constructor used to create the allocate the memory for this DFFCG. Okay, what will happen in the environment when I call in TB, when I call env.run, automatically it will call all the run tasks which is present in this command. And if you see, except the generator, everywhere I use forever. So continuously it will checking. So when it start to send the transaction, generate this transaction, it is put into the mailbox automatically. This driver will get, okay, and it will convert into pin level, and monitor will also check continuously for any signals we are receiving at the interface. And it is received, will convert into transaction, and it will put into the mailbox. And checker scoreboard also checking whether any data is there in the mailbox. Okay. So these are the blocking methods put in it. So when you put, it will get. Then run.do5. Here you can write a command so that automatically when you call this run.do, this steps will be happen. Okay, log vlog. This is for elaboration. Vlog top.sv is nothing but the top model file name. When you call this, compilation will happen. It will start compiling this file. So here you need to mention the file name in an order. Order in the sense from lowest to highest order. Okay. For example, tx we are using in all these files. So when you put these files before tx, the compiler does not know what is tx. Another example, if you see environment, inside the environment we are instantiating these components. Okay. When you put environment before this, the compiler directly go to the environment. It does not know what is checked or what is covered or what is generated. So when you compile all those things, you need to compile environment. Once environment is compiled, then final TB program block. Okay, then the top model will get compiled. So once compilation is done, then this is the for elaboration. So we see -o here. Top is nothing but the model name of this top. Here, this is the test case name. So, whatever the name you are giving here, that name you should use here. So, plus test case. For that, I am assigning right it. I have only one test case here. I created as right it. Now I am passing this test case here. So automatically the test will happen. And this is to add the waves, add the waves. Okay, I am adding only the signal to waves and one not to start the simulation. Okay, once all these files are created, we need to give, if you are doing first time, there is no work library inside this directory. So that you need to create delete work, then after this map vmap, so that work library will map to the work library which is created. After that, okay, we can enter to lesson 2 with the help of using command. It will take some time. Okay, all the commands which is written inside the run.do, you can step by step you can mention here. Okay. Or else if you put into run.do, okay, when you call do run.do, automatically so this compilation happens for the log. After that vsync command is running now. Okay. Once it is simulated, it will show finish. Okay, as you should want to finish. If you give yes, it will quit from this. You should do no. So this is the simulation output. You can see reset undo and queue. Okay, once reset is released, at each passage of clock, here in the interface, if you didn't mention anything, okay, this input skew values as 1 step and output skew is as 0. So at passage of clock, it will capture just before the passage, it will capture the value. Okay, here it is x. So in output, we are getting x. Here it is 0, output we are getting 0. Here it is 0, output we are getting 0. 0, 0. Here it is just before the passage of clock, up to 0 that we are getting the output. Here it is 1, we are getting 1 here. Then in log file, this is the display we written inside the checker. So there are all the inputs are matching with the output. Then to see the coverage, inside the tools we have coverage report, choose HTML and you OK. The coverage report will be created in the HTML format. Later, if you want to see means you can use Firefox that file.html. Here you can see inside DFF cover. There's a cover group. If you click, you can able to see the cover points. So inside that you can see how many times bins got hit Okay, what are the bins covered and what are not covered, all the features you can see in this report. So then, if you are using VDA playground, all are same. Coding wise, everything is same. Design you are writing on the right hand side. There is the test bench components developed. So here design is inbuilt. It is linked with this test bench. So here I create a separate file. So I included here. If you write in this design.sv, you need to include that here. And in the top, we need to give this line to dump these signals so that you can get the waveform, $dump file and dump as. And choose this LDEC tool, and you need to enable this run.do and EP wave after it. In this run.do, these commands you should write. Okay. It is applicable only for LDEC to get the coverage report. So the coverage report is generated in an ACDB format, and this is converted into text format, and it is displayed in the log file. You will get the coverage report here. In coverage, there is option per instance equal to 1. So you should give this as 1 so that you will get the details in the log file. Then you can able to see the waveform. You enable this. Open EP waveform after. That's the difference between using media playground and training servers. Okay. That's all. Thanks.